All right, finally, lesson 13. Well, it's not really finally. We still have another 3 after this, but at least we're nearing the end. And this is on 2 sort of application areas of interest to at least me and many people. The Internet of Things. That's a really broad, increasing field of which we really will touch on in this lesson. And the other one is sort of science clouds, which we'll have examples of in the physics application, and remote sensing, and there are, of course, lots of other applications. Astronomy is one, and environmental science are all big data applications. So this is big data applications and analytics. We're in the School of Informatics, Computing, and Engineering. And this is the course motivation, lesson 13. Thank you very much. All right, let's look at how scientific computing gets done. So we have various forms of scientific computing. We have large-scale supercomputers. Blue Waters at NCSA, Illinois is a good example of that. These come often now with GPUs. They run highly parallel simulations. Maybe they're up to 1 million cores or so. And they have customized networks, no latency, high bandwidth networks. They have, of course, multi-core nodes. And those take a few jobs, decompose them over the supercomputer, and do large-scale parallel computing. They're so-called high-throughput systems, which do what we will sometimes call pleasingly parallel jobs largely. This is what used to be called the European Grid Initiative, in the US, the Open Science Grid. And they can often do cycle sealing, whip off to a largely idle machine and find spare cycles on it. And the analysis of the Large Hadron Collider is a very good example of how this is done. And as I mentioned, this uses hundreds of thousands of cores around the world to do their analysis. Then we have grids. Grids, by definition, distributed systems. They take resources, such as those of OSG and EGI across the world, and federate them together to be able to harness multiple computers to solve not a closely covered parallel job, but typically lots of jobs with a similar goal, just as lots of jobs analyzing data from the Large Hadron Collider, which data can be typically the detailed compute-intensive analysis is largely independent. Everything in the world uses services, both commercially and in science, and typically software as a service is used, although it may not be advertised according to that fashion. Now, the key idea is portals, which is where you access these machines. You typically build a portal to access it. And we have workflow, which integrates lots of processes into a single job. And you typically always have workflow. In any commercial job or any science job, workflow is almost universal. It's sometimes called orchestration. But whatever its name, it certainly is used a lot. All right, now let's see how clouds fit in. So HPC systems have the lowest synchronization cost and the highest communication capability. Grids have the worst, because grids are typically distributed over the world, so they have long delays just from the communication time. Clouds are in between. They may or may not be distributed, but in any case, the virtualizations that they tend to use, and the fact they are virtualized, namely whether or not they use hypervisors, virtualization makes it difficult to keep nodes together. And remember that the node is next to each other, which is key in high-performance computing. To get good performance, you exploit the locality of the system. So there is a sort of hierarchy. Grids are the least coupled, then clouds, and then classic HPC systems. So this says that clouds can do grid workloads. Particularly, they can do the Large Hadron Collider analysis. However, they're not so clear for closely coupled HPC applications, although many people are working on making clouds more effective. There's technologies like SRIOV, which allow you to remove the synchronization overhead, so that you're still faced with the problem that as soon as you do any logical virtualization, it's not so easy to keep locality. So you can always say high-performance computers are HPC machines. They typically run in the so-called message passing interface parallel programming model, where the user does the parallelism by hand, and the processes, which are the decomposed parts, send messages through with MPI, and they offer the highest performance on closely coupled problems. So you can actually look at this, we'll see at MapReduce and MPI, and look at this hierarchy, map only. That's the pleasingly parallel case. The classic MapReduce, which is done in the basic version of Hadoop, a single map followed by a reduction using disk to communicate between those steps. The use of the disk gives fault tolerance, but slows down the system. Iterative MapReduce is used for data mining, such as the expectation method, maximization methods, and clustering. It caches data in memory between iterations and does not write them to disk. And it also supports high-performance collective communication, such as reduction, scatter, gather, broadcast, multicast, and so on. Then we have classic MPI, which supports small point-to-point messages, which you get in simulations. It's typically a rather different message structure for data mining than simulations. Simulations tend to have lots of small messages because you have particles, say, spread around the nodes of a simulation engine, because those are the particles you're simulating. Those particles tend to interact only with a few nearby particles, and those few nearby particles they have to send message to if they're in a different node, and that leads to very many small messages. So what happens, what works in clouds? Well, certainly pleasingly parallel, or we can say somewhat more general and pleasingly modestly parallel, and roughly independent data. This clearly supports the long tail of science, which is largely a lot of small jobs, and also the integration of the distributed sensors, or more generally the Internet of Things. We're going to discuss IoT a bit later on. We also know that things like recommender engines and search algorithms run amazingly well on MapReduce. That's because they're not iterative. However, we know that we can change MapReduce to iterative MapReduce and do other data analytics. There are not so many great examples of science applications using clouds. There was a nice project from Microsoft funded by the European Union using Azure, and they did 27 applications on clouds. FutureGrid, which is you could say is a academic cloud, did a lot of cloud applications, and most of those were from life science. At least half of them were, not most, but 50% is larger than the fraction of science. I mean, life science is not 50% of all science. I note that locally, the Lilly Corporation is actually a big commercial cloud user, but the academic part of Indiana, namely Purdue and Indiana Biology, I do not think use cloud significantly. And in general, there's not a lot of academic science use of clouds at the moment. It's not just the technology issue, there's some business issues, because NSF supplies funding to users to use certain classes of machines, and that money is not so easy to use on Amazon or Azure, which require money as money, not money as an NSF promise to support. So if we look at parallelism, we can do parallelism over users. That's the long tail of science. And we also, that's one type of parallelism we can run on clouds. In particle physics and astronomy, particle physics collects events of particles colliding. Astronomy collects images gathered by telescopes, snapping the sky. These produce a stream of events or images which can be run well on clouds. So in the long tail, a good example of the long tail is genomics and environmental science. which gather in the distributed fashion data, and this data is nicely integrated, this analysis on the cloud. And as I mentioned, we can either do the map-only version of MapReduce, just running computations, or we can do map followed by reduction, where the reduction is typically collecting many jobs together, such in the case of the discovery of the Higgs boson analysis. We want to be able to collect all the events together to plot them in histograms, and that's a typical use of MapReduce. And so often reduction is just used to summarize multiple maps, but the main computation is in the maps, and the reduction is a rather quick final step to collect together final results. Docking is another example to try to looking at which proteins dock into each other, which chemicals dock into proteins. That's again a pleasingly parallel application running through proteins and chemicals. Now we come in the last parts of this, last half of this lesson to the Internet of Things. And there are various estimates which depend probably on the way they define what a thing is. And they say from 24 to 75 billion devices will be on the Internet by 2020. Most of these will be small sensors. Many of them will actually be in smartphones, because a typical smartphone has, I don't know, 10 to 12 sensors. And those sensors which measure acceleration and cameras and GPS location, etc., they stream information from the sensor into the cloud. And you see that every day you use your smartphone, you're seeing that. And the cloud will not only respond to that particular smartphone, it will actually integrate the data from lots of smartphones to get some global picture of what's going on, which will help in other types of analyses. And so the cloud is a critical controller for the Internet of Things. It also is a resource provider, because when I do a search on my smartphone, I'm going to the cloud to do the search. So we have all sorts of ways of representing the fact that the world will be full of tiny computers. Remember, I pointed out that Moore's law said CPUs are getting smaller and smaller, so you can sprinkle them around, smart dust, and you can have intelligent rivers and smart homes and smart grid, ubiquitous cities, the Korean term, and we also expect lots and lots of work on robotics. And some of this Internet of Things will support science. And these things are very naturally parallel. Everything can be processed largely independently in this basic step. And clouds are super suitable for processing things, because clouds love to produce lots of independent things, because the synchronization overheads which clouds have is irrelevant. And also note the things themselves are actually a grid. What centralizes the cloud, and that's not necessarily good. It could be a grid, but it's not, you don't really know what's going on inside a Microsoft or Amazon cloud. But the things are a grid. So you have a sensor grid supported by a cloud controller. If we look at the use cases, we'll see we have an important characterization of ones that are streaming. And we'll see lots of examples of this. You could, a good example is Twitter data. Twitter data streams from users into Twitter. Actually the data from smartphones, or the different devices in smartphones streams into the cloud. So there's an important concept of streaming data, and that streaming data is typically can be processed with other algorithms. And in fact, even people are streaming, because when I not only would tweet, but when I just actually do search, I'm streaming my search, or I'm streaming my e-commerce transactions, and that's a pretty important type of application. And there's a piece of software called Apache Storm that is very critical here to integrate this these different streams together and produce some coherent approach to them. You can, for instance, find automatic dynamic clustering of Twitter streams, tweets in this fashion. And then we need to look at the new algorithms which actually update, say, the cluster, in the case of that Twitter data, update the clusters quickly and produce new clusters or new cluster centers and new cluster properties in a dynamic fashion. Very exciting area. Streaming data is very, very exciting. And here we have some from KPCB, Mika, the standard picture of the growth of just now here from 2006 to 2013 of these MEMS data, micro electromechanical systems, and notice that mobile phones are the largest. Here we are, mobile phones, the blue things, the light blue. Then we have media tablets, headsets, laptops, wearables, expected to be a huge source, and and some from gaming as well. So anyway, there's a lot. This is the current source of the Internet of Things. We're expecting smartphones, which are dominant now, to get competed with by things like the industrial internet, the smart home, the ubiquitous city, and so on. These things which spread things around devices around the world, the critical infrastructure of the world, are likely to dominate over smartphones because smartphones are limited by people. And there are lots more places, and people just move around, whereas to sort of put statically instrumentation, things all around our homes and cities and roads and things, is likely to happen in a way that we haven't quite seen yet. And actually, that's been predicted to be more important than it is because people have not found either the killer application or the killer integration into a convenient application. Here from Business Intelligence is a nice plot of the expectation for home devices. Home devices is an area which, again, it was meant to be very important around 2000. I brought lots of books on the subject, I think a little before that, and I tried to look into home automation, and I did not do anything probably correctly because that was just not ready to be used. And there's expectation that this will increase. Google is well known to have bought this company Nest, which makes smart thermometers and things like that. And that's sort of promising, but has not really taken off yet. This is my picture pointing out how the clouds controls. Here's the cloud, and here are all your sensors. Here's scientific sensor. Here's that sensor might run on an aircraft. Here's a connector, a smartphone, a Lego robot, and a webcam, and they're all feeding into the cloud. And that's what I call sensors as a service. And those sensor processing as a service, which is, I pointed out, done through Storm. In this case here, is designed for this glaciology remote sensing data, which we'll hear about at the end of the course. That's, if you like, sensors as a service is running the software to process the raw data from the sensors in the cloud. Here is another example from Mika, which is self-driving cars that uses deep learning to analyze the results of the images and make decisions on how to drive a car in a very effective fashion. So that's cars are themselves full of hundreds of, every car today is full of hundreds, or probably, I don't know how big, it was even hundreds a few years ago, maybe much bigger now. Lots and lots of computers in every car. Smart vehicles. Here we have, of course, drones or another. Here's a nice drone, a hexacopter, or I don't know how many things there are there. And those are, and here we have a more traditional drone, aircraft drone, and they're for agriculture, sports and entertainment, and also for search after disasters and giving immediate first aid response and things like that. So that's believed to be a very important area. And we know Amazon has suggested that we use drones to deliver, and the FAA is complaining that this is all very dangerous and they have to put a stop to it because it might be progress. We'll have to see what happens. And here we have another example of things which are, I mean, this is actually Apple Pay, which just came out as a good example of this. But today I use this when I go on the aircraft these days. I just have my boarding code on my smartphone. And I just try to avoid my stupid smartphone automatically switching it around so it becomes unusable. But in general, it works fine. And Starbucks is certainly a well-known place that does this, but lots of people are doing this type of smartphone-related scanning, and you can get information on products and prices, nutrition, and so on. And of course, UPS trucks and things are all automated through this type of scanning. So this is the Internet of Things, which is going to get more and more important. And I already mentioned right at the beginning of this motivation how every GE engine is full of devices, and GE claims, at least a couple of years ago, to generate about 10 times as much data as Twitter does every day from the things inside their engines, which allow them to do better maintenance, and so on and so on. So this is all pretty exciting. All right, we have another specialized hype cycle here, the one for the Internet of Things. And we can see things we've seen more already, IoT platforms. Actually, these are general things, machine learning with the Internet of Things itself, processing all the data from the Internet of Things, which is event stream processing. Architecture of IoT. How do you put all these devices together? Connected homes is obviously, I sort of see that in a different way. It's a dominant product. IoT for customer service, IoT edge architecture. That's sort of almost the same as IoT architecture. Services you need for the IoT. Digital ethics. That's sort of an edge analytics. Quite what those are, I don't know what the words mean, why they're singled out, I don't know, because edge analytics would be built by machine learning and event stream processing and IoT platforms. Security, digital twins, we'll discuss that a little. Things as customers, replacing people by things, which, because they ought to be interchangeable, because people manifest themselves by tweeting, where they look just like a thing, producing some data. MQTT, message queue telemetry transport, is just a protocol for how you communicate with things. It's I don't so certain it's actually that good, but it's certainly very popular, and comes from the intelligent machine telephone world. Machine-to-machine communication, that will perhaps use MQTT as the protocol. Smart lighting, those are advertised all over the place. And so here is, again, the purpose maybe of these hype cycles is not to study them so much in detail, but just to see the types of things that Gartner thinks are important for the Internet of Things. I think it's much harder at this level to rank them and to get a coherence than it is at the higher level, where the ranking is and the status is much easier, I think, to understand. All right, now we have a subset of the Internet of Things, wearables. So smartwatches, sports watches, which was sort of, we know that putting things on your wrist was first done for health and sports applications. Wristbands are a sort of special case of a sports watch. And over here we have, intelligent shoes or something with things built into their soles to monitor what the pressure and things like that, and head-mounted EEGs, again for reading out automatically from patients' blood pressure, skin patches, all sorts of, and here are wearables coming from 3D printing. That's sort of quite common these days. And so these are all the different types of wearables, of which smartwatches and wristbands and head-mounted displays, which is what you need for AR and VR. These are perhaps the more important of these areas, with the other things like smart footwear or smart clothes, which are here up here, smart garments, and they're all part of the evolving smart dust. You just spread whatever you have in the world. You just spread internet active devices on them, so that you can measure everything under the sun as they get used. Digital twins, which is basically computational science. It is that a model of a physical thing that is used to use its sensors to understand its state, respond to changes, and improve operations. So this is somehow making a model or simulation of a set of, let's take a car. You could build a digital twin of your car and use that to design a better car, or possibly to, in real time, feed in the sensors and use the digital twin to make a prediction as to what will actually happen. Will the car really be able to make that tight turn, or is that impossible for its mechanical engineering and power? So this is actually something I hadn't really realized, that 3 to 5 years, billions of things will be represented by digital twins. And maybe even aircraft engines will have digital twins, because we know they're pouring sensors from engines into the cloud, and their GE and Rolls-Royce and people are using that sensor data to know what's happening to the engine, which could certainly well involve simulations of engines. So here again, that's certainly the aircraft engine application is service and maintenance, proactive maintenance is a very important area. So it seems that they think it will take a while to get going, but this is a critical technology. I must admit I had not heard of digital twins until I read these Gartner reports. Personal devices. So this is a sort of prediction of what will happen in the wearable world by Gartner. 14 billion personal devices, wearables, and other consumer IoT endpoints. So maybe a sensor on your head or something. 2020, there'll be 6 billion things shipping. That's actually a relatively low number compared to some of the estimates in the past. 2/3 of them for consumers. Voice will get more important. We've done that already. And these Alexa-style virtual personal assistants, of course, we learned that Google was better than Alexa at the moment, but Alexa's actually doing better because she has these nice speakers which she can look after. And then you'll do biometric-assisted technology for people in risk, military people, heavy machinery, and things like that, people in dangerous situations. And people will try to keep their employees healthy, and they'll like to have fitness devices put on all their employees to see what state they're in. So here is a chart from IDC of the sales of wearables. Let's ignore the percentages because they don't appear totally consistent. Maybe they have some significances which is not somehow consistent with the numbers shipped, because obviously, so 31.5 million shipped to the Americas and 47 million shipped to China, India. I said, oh, that's sort of plausible, but 31.5 is not 4.2% of 97.3 million. 47 is not so far off. 46.8. It's not the same, but it's nearish. So let's ignore the percentages. Maybe somebody can think of what they could be. But so you can see reasonably broad interest in wearables, with particular interest in Asia and the North American continent. Then we have some comments on IoT platforms, which is actually where I work. We have this project called IoT Cloud, which we licensed to a Canadian company, C2RO. And Predix is the most famous IoT platform. It's a secret because it's produced by GE. It's not obvious what it does, as far as I know. It's not so difficult to reproduce Predix because I think it's built around the standard Apache stack. But it's important to realize how much money this represents to GE, because they have a lot of their IoT devices are installed in their machines, because they make refrigerators and engines and motors and things like that, air conditioners probably, and all of those have sensors which can report back to GE Central, and so GE Central can find out a lot of very useful information. There is an earlier slide that points out that GE engines produce more data than Twitter. So there are 200,000 assets which are being managed by systems like Predix, and they have 20,000 developers working on this problem. So they're GE, which is sort of the classic US engineering company, it's a software company. And they found Predix gave them 500 million. So maybe we can get 10 cents from our platforms. The cloud vendors, they mentioned Microsoft here, but Amazon has its lots of offerings. It has Kinesis, which is data streaming system, which is really the leading streaming data system, although Azure has a similar offering, which is quite effective, which is not quite as famous as Kinesis. And here is this IoT platform. It's meant to be 100 billion today, and it's growing up to, or maybe over 100 billion today, 150 more, growing up to over 300 in 2021. Pretty large dollar volume. And here we have the last slide. Only for nerds like me, this is the actual transport protocol, which is used by IoT systems. And we already saw MQTT, it was on the hype curve, but HTTP is actually more important, which is not too surprising. It's the dominant messaging transport on the web. AMQP is a very famous publish-subscribe messaging system. So here we can't even spell proprietary, but never mind. Let's add an R there. And I'm not quite certain what CoAP and DDDS is. XMPP I have worked on, but although I've forgotten its details. Anyway, this just points out the two dominant things, and whether they're the right ones in IoT cloud, I don't think we use either of those. We tend to use the pub/sub standards, publish-subscribe system standards, because you always tend to use a equivalent to publish-subscribe in IoT systems, because you have erratic events generated going back to some other system like the cloud. The cloud sends an erratic control message back to the IoT, and so you need the queuing, which is implicit in a publish-subscribe system, to be able to process that. All right, that's it. Thank you very much. This is the end of this lesson. Thank you.